We've talked about acceleration already a little bit because we've talked about velocity versus time graphs. Okay, and we know that on a velocity versus time graph, like the ones we got yesterday in our lab, okay, if they look like this, the object is accelerating in a positive direction, or it is increasing its velocity. Okay, so we have to remember that in physics, acceleration can mean any change in velocity, positive or negative. So even slowing down is still an acceleration. We don't use the term decelerate. Okay? Any change in velocity. And that, in fact, believe it or not, includes a change in direction. Okay? Can mean that an object is still accelerating. Okay? Like oddly enough, I just got done teaching my physics 20s about this. Okay? And this is going to seem a little bit counterintuitive. Okay? But if I've got this tape whirling around and around in a circle, it's accelerating, even though it's traveling at a constant speed. How's that possible?
Because it keeps changing like directions, kind of.
Exactly, it keeps changing direction. The definition of acceleration is a change in velocity, not speed. Speed is scalar. Okay? Certainly if an object accelerates, its speed could be changing, but if an object accelerates, its velocity is always changing. Okay, does that sort of make sense? So it's important to remember that the definition of acceleration is any change in velocity. That includes if all you do is actually change your direction. You don't actually have to go faster or slower to be accelerating. Okay? We talk about this in physics a lot in regards, especially this time of year, which is when it always comes up, when people end up in the pond out here. Okay? Because in physics, we're savage. Okay? Like there are no holds barred. If you take that corner and you're drifting it, or you're just going too stupid fast, okay, and you end up in the pond, you are a physics question. Okay? You are the example for like the next 5 years. So-and-so ended up in the pond. Okay? Well, the reason they ended up in the pond was in order to turn that corner, you have to accelerate. Not go faster. That was the mistake they made. Okay? Not go faster, but change your direction. In order to change your direction, a force has to be applied. Okay? So if you want to go faster, you press the accelerator and the engine applies force and the car goes faster. If you want to slow down, you press the brake. The brakes apply force and you slow down. If you want to turn, you don't use a pedal. I mean, you should brake first. I mean, not much is obvious, but hey, you don't have to have your foot on the brake or the gas to turn. So what makes you turn? What keeps you from sliding? It starts with F. Friction. What is there not on an icy road? Friction. Okay? So when you turn that corner, the force that makes you accelerate, that causes that change in velocity, which is only a change in direction, is friction. Okay? When there's less of it, you have to go slower. That's a good life lesson right there. Okay. All right. What's people's number one reaction? Or what are their two natural reactions to going into a corner and sliding?
Oh crap.
Oh crap, which usually implies two things.
Don't they like around the steering wheel, try to steer out of it?
Yeah, well, you're supposed to try to steer out of it, but when we go straight and we're trying to turn, our natural reaction is to crank the wheel more. It's not doing what I want, so I should turn it more. Okay, is that what you should do?
No.
No. Okay, you should actually try and steer less. Okay, so that your tires can start to turn again. When your tires turn, you actually have more friction. Okay, it's static friction versus kinetic friction. Okay, it provides better turning ability. Okay, and what's the other reaction?
Slamming on the brakes.
Slamming on the brakes, which does what to your wheels?
Locks them.
Locks them up. It doesn't matter if you have anti-lock brakes or not. Okay, if you're sliding and it's that slick, they're just going to go tick, 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 and you're going to go straight. Okay, so you have to get off of the brakes. Any of those things will get your wheels turning, increase the friction that can allow you to accelerate around the corner. Okay, so in physics, when we get to that lesson, we'll watch all these videos of Canada's worst drivers doing exactly the wrong thing, okay, and ending up going through the styrofoam walls.
How does hydroplaning work?
So in hydroplaning, what ends up happening is you've got water that, it doesn't have to be super deep, but if your tire treads are not very good, your tires are bald, your tires will actually sit on top of the water, okay, which has way less friction than if they're in contact with the road. So you actually sit on top of the water, and now you can't steer, right? Because it's like trying to steer a boat with a brick. Okay, as opposed to a rudder, right? Like if you had a rudder, you might actually be able to turn the corner. But yeah, once you get up on top of that water, then yeah, your wheels just turn, right? They just spin and they don't do what you need them to do. Right? So tires have treads on them in order to push the water out of the way in the summertime, and in the winter they actually have tread that looks different to help grip on ice, but it still wants to pull water away. So if you've ever looked at your tires, okay, especially on winter tires, they've got these little, they've got big blocks, big traction blocks, and inside those blocks are little squiggly lines. Okay, you guys ever seen those on your winter tires? Okay, those little lines are called sipes. Yeah. Okay, now what the sipes do is when your tire starts to spin on ice, it melts the ice. Okay, and it makes a little layer of water between your tire and the ice, which is worse. It's like hydroplaning. Okay, so these little sipes, when your tire is flat against the ground, the sipes open, and because water is a polar molecule, it gets pulled into the sipe. So it pulls the water away from that interface and gives you better traction, okay, on the ice. The reason that works on winter tires is winter tires are made of a softer rubber, so they're more pliable in the cold weather. If you leave all-season tires on your car, they actually get quite hard in the cold weather, to the extent where you can actually feel, if it's like minus 35 outside and you have all-season tires and you've been parked for like a few hours, you can actually feel the flat spot on the bottom of the tire, okay, because it hardens against the ground, and until it warms up a little bit, you can actually feel the bump as you're driving along. Okay, so winter tires are made of a softer rubber and they have different tread pattern to help with those kinds of conditions.
You know those little like rubber things that come off of it? What are those for?
Little
like,
rubber.
Like they're little tiny.
Oh, the little yeah, they just stick out on a brand new tire.
Yeah.
They're just from the mold.
Oh.
Yeah, it's like the mold. They just pour liquid rubber into a mold, let it cool, and then pull the mold away. So those are just a product of that. They just wear off.
Okay.
Yeah, they're not really for anything. They're just the byproduct of the process they're made with.
My mom has all-season tires.
Mhm.
During winter times, we always the tire always gets flat. I don't know.
Could just be that, like maybe where the valve stem where you fill it up. Sometimes when it gets cold, and it can happen even on winter tire, happened on mine last year, that the seal just doesn't get very good when it gets cold and it contracts, it just leaks a little bit. Yeah. Or maybe there's actually a small hole in the tire. I actually noticed this the other day because I just got my tires changed. I'm like, oh, my tire's flat. I'm getting it changed on Saturday. I just kept pumping it up. And then I actually found the screw that was in it. But if I was out here parked in the cold weather, it didn't leak because the tire contracted around the screw and it didn't, but if I was parked in the garage, I could hear it hissing, right? Because, just whatever, the expansion or whatever, it just didn't fit quite the same as when it was cold, which was backwards to me. I thought it should leak more when it's cold, but for whatever reason it didn't. It just leaked in the garage. So yeah, could be any number of things. Just in cold weather and everything contracts and gets hard, it doesn't seal as well. Yeah. Okay, is that sort of making some sense? All right, so we already know this formula here a little bit. It's written a little bit differently here. On your formula sheet, it does look like this, and this is the way we'll use it most. Okay, acceleration is VF minus VI over T. Okay, we often write that delta V over delta T, change in velocity over change in time. Okay, so that's the formula that we'll be working with today and probably Monday. Okay. So what it tells us is that the more you change your velocity, the greater your acceleration. Agreed? Okay, what if I change my velocity a lot, but it takes me a really long time? Is that a high acceleration or low? Probably low. Okay. What if I don't change my velocity very much, but it doesn't take me very long either?
High.
Could be high then. Okay, so two things can affect your acceleration. How much you change your velocity and how long it takes you to do it. Okay, it's this formula here that all safety devices are kind of designed around. The greater your acceleration, the greater the force you will experience. So anything you can do to change your change in velocity or change your change in time can affect how much force is exerted on you. All right? So obviously brakes on a car are designed to reduce your initial velocity going into an acceleration. Like let's say, you're driving along and somebody just runs a stop sign. They're going through an intersection. You're going to collide with them. Okay? Your natural reaction and correct reaction is to slam on the brakes. That way, at least when you hit them, you're not going as fast. Okay? That's going to mean less acceleration after you hit them. Okay? That's going to mean less damage, less injury, all of that kind of stuff. Okay? Once the collision happens, all the other safety devices in your car are designed around this part of the formula. Because the change in velocity part, none of them can change. The collision is going to happen, the final velocity is going to be 0. All you can do is change the initial velocity. Okay? So, the other parts of your car are designed to make the crash take more or less time? More. Believe it or not, you want the crash to take as long as possible, because the bigger T is, the smaller A will be, right? And the smaller A is, the less force you will experience. Okay? So your car is designed to self-destruct, right? It's designed to crumple up like a tin can. Okay? By crumpling, that takes time. If it was rigid, the crash is done. You hit and that's it. Okay? The crumple makes the crash take 1/10 of a second longer. Okay? It doesn't seem like much, but every little bit helps. Okay? What about your airbag? How does that help?
So you don't go through the windshield?
Well, no, your seatbelt keeps you from going, you'll go right over top the airbag. If you're not belted in, you'll go right over the airbag and out the windshield anyway. Okay? The airbag, what letters are written on your airbag? SRS. Supplemental restraint system. Supplement means not doing it on its own, it's in addition to your seatbelt. Okay? Your seatbelt is the primary restraint system. Okay? So the airbag helps to prevent head injuries. Okay? Back in the day, like even in my generation, okay, if you got in a car accident, lots of people would have the same scar. It was a scar that ran right along your scalp, right here. Okay? Because when you got in an accident, your head would go forward and it would hit the steering wheel. Because airbags weren't a thing then, that's how old I am. Okay? And steering wheels were hard. Okay? I mean, they seem like they're hard now, but they're actually designed to cave in and go away from you in a crash. The whole steering column is collapsible. Okay? So if you were to hit an old steering wheel, you just got your head, you got scalped. Okay? Like you would hit it and everybody had the same scar, it was the steering wheel scar. Okay? And it would peel your scalp back a little bit. When you would hit it, everyone had the same one, and you get a really bad concussion or maybe worse, okay? Because that's what you would hit. And partially because also old cars didn't have a chest strap, right? They just had a lap belt. Okay? So your head would always pitch really far forward in a crash. Okay? Whereas now with a chest strap, you go forward, you hit the chest strap, now your head goes forward but doesn't impact anything other than this. Well, don't get the idea an airbag is a pillow. Okay? An airbag is still a punch in the face, okay? But it's not as bad as hitting a steering wheel, which is rigid. Okay? It's an explosion. If you've ever been in an accident where the airbags go off, like your ears will ring for days. Okay? It's 120 decibels and it's right in front of your face. That's how it inflates so fast. Okay? It's not like someone's sitting there with a pump pumping up the airbag for you. Okay? It's literally a chemical reaction that causes an explosion of gas into the airbag. So it does, when it hits you, like if you're driving and it goes off, you'll have bruises on your arms from the airbag hitting your arms and throwing them to the side.
Aren't if you're in the passenger seat and you have like your leg up on the spot where the airbag is and it comes on, doesn't it just like send your knee through your face?
Yep, you can break your leg. Also why you shouldn't put rear-facing car seats in the front seat. Okay? You're never supposed to have small children in the front seat because the airbag can hurt them in a crash. They're to be in the back seat.
My dad told me that you should never drive one-handed, because then if you ever get in a crash, when the airbag comes out, apparently
To punch you in the head?
no, it'll put your knuckles through your skull or something.
I don't know if I buy that. Because that's how I. But I mean, like it's gonna throw your hand back at your face. But I mean, there's a lot worse things that are also going to happen. If your airbag goes off, you're in a significant crash. Okay, I've been in a couple of accidents, and I'll say one of them was my fault. Okay, but the other ones were not. But I've never had an airbag go off. They've all been at low enough speeds, or because they have the most important safety feature in any vehicle, mass. Okay, I win. Okay? Make no mistake, in every crash there's a winner and a loser, and the loser's always the smaller car. Okay? And if you have a big vehicle, you get to win more often. That's why you never see a semi-truck lose a crash. Okay?
No.
So mass matters, because this other thing that we were talking about here, how acceleration leads to force, okay? Well, mass, okay? Bigger mass means less acceleration, okay? The force is the same. A semi-truck hits a smart car, they feel the same force, believe it or not. It's Newton's third law. Every action has an equal and opposite reaction. When a truck and a smart car hit, the forces are the same. What's different is this, okay? Because this is also very different, okay? And so, yeah, the bigger vehicle is always going to experience less acceleration because it's simply bigger. So I'm willing to put gas in my bigger vehicle for the sake of having the added safety feature of mass.
Did you say like the back seat without your seatbelt? Like what, you just hit the
You'll hit the front seat. It's actually quite dangerous, especially like if there's any spinning or rotation in the crash, because then you become a projectile in the car. Oh, I kid you not. Like there are lots of times, like how many people have their pet in their car with them when they drive? Is your pet belted in? Do you know what kills people who have their pets in their car? Their pet. Okay, like we have a thing that goes into the seatbelt that attaches to our dog's harnesses. Okay, because if we got in a crash, I mean, we want our pet to be safe, but we also want to be safe from our pet. If we crash, the pet keeps going, right? And then they're moving around the vehicle, and they can hurt you, okay? Just because they're moving around, right? Any debris in the car is going to move around. That's why you see lots of people that have like a cargo net. If they have like a hatch and they have lots of stuff in it, they'll have a net between the cargo area and the passenger area of the car to keep anything from moving forward. If you crash, everything keeps going. That's Newton's first law. It's called inertia. It's the first thing in this lesson. See how I come back to that? Okay. So inertia is the tendency of an object to remain at rest or an object in motion to remain in motion. Okay? This is why you need to wear your seatbelt. If you don't wear your seatbelt and you get in a crash, your car stops. You keep going until acted upon by an external unbalanced force. Windshield, hood, other cars, the ground, things that are bad. Okay? That's why you have to wear a seatbelt. Okay? You don't want to continue moving at the velocity you were already moving at. Okay? You want to do what the car does. You're much safer to stay in the car. Right? And I mean, you hear all these people like, well, I don't want to wear a seatbelt because, if I get ejected from the car, I'll be safer. No, okay? Because they've heard of this one person in a million who got thrown free of the crash and survived. Okay? And especially in rollovers, there's this idea that if you're not belted in, you'll be thrown out of the car. Yes, you will. Okay? So when your car is rolling like this, when are you going to get thrown out? You're going to get thrown out as the car is going this way. I guarantee you, flying through the air, you will move faster than the car rolling along the ground. Guess what? The car will roll over you. That's what happens to people who don't wear their seatbelts in a rollover. they get thrown out at the top of the rotation, fly through the air, land on the ground, are knocked unconscious, and the car rolls over. You can't beat physics. It just happens. You just have to, well, do the right things, like wear your seatbelt, okay? Not take icy corners too fast, okay? Drive like a sane person, okay? All of those little things, okay? So there's lots of application to this acceleration stuff. Okay, so as we were saying, when we started all this and the people ended up in the pond, okay, their tendency is to keep going at a constant velocity, which means they would go straight, okay? A force has to be present to cause an acceleration that changes their velocity, okay? Newton's first law says, in the absence of any forces, your inertia is to keep doing what you were already doing. So if you were moving in a straight line, you're going to keep moving in a straight line. Okay? If you're sitting still, you're going to keep sitting still. Okay? Perfect example of Newton's first law. If I don't do anything to this cart, it will stay right there. Right? Its inertia is that it's stationary. It would require an unbalanced force to change that. Right? An unbalanced force will cause a change in its velocity, and it starts to accelerate. Right? It went from 0 to something else. Okay? So, that's very basic physics. Newton's first law. Okay?
Well then, is like gravity a force?
Gravity is a force.
So that's why, like, if you throw a ball or something, it's never gonna like just like keep going forever.
Right. What comes up must come down.
Yeah.
Yeah. Okay. So
And then eventually it stops rolling.
eventually it stops rolling. Yeah. Like right now, how many forces are acting on me right now?
A lot.
1, 2.
2. The obvious one is gravity, right? Gravity wants to pull me down into the floor. If
Pressure.
gravity was the only force, it wouldn't be balanced, and I would be doing what? I'd be falling. Do you accelerate when you fall?
Yes.
Okay, I'm not accelerating right now. What's keeping me from falling?
The floor.
So what's the floor doing? Pushing back up. Newton's third law. Every action, I'm pulled into the floor, has an equal and opposite reaction. I'm pushed back up by the floor. Okay? If I stood on a bathroom scale, okay, the scale would tell me how hard gravity is pulling me down into the floor by telling me how hard the floor is pushing back up on my feet. Okay? Well, it actually doesn't usually say that. When I stand on a scale, it usually goes, get off, get off! Yeah. All right, so acceleration then, okay? Acceleration is, like we said, any change in velocity, okay? And we're most concerned with this version of that formula, okay? What we're gonna do today is look at different manipulations of that formula and just gonna do some problem solving, okay? Everybody all right with that? We got a good look at how that all applies in daily life, okay? And because it does, it's huge, okay? Acceleration is something that happens all the time. All right, so let's imagine kind of a simple scenario here where, okay, we have a plane that starts from rest. Okay, this word's going to be important because it comes up all the time and it represents something for us. If I am at rest, am I moving?
No.
Okay, so if I start from rest, my initial velocity is
0.
What if I come to rest? Then my final velocity would be 0. Okay? If something comes to rest, then it has slowed to a stop. Rest always means 0. You just have to determine whether it's starting or ending at rest to determine whether VI or VF is 0. Okay? But rest always means 0. Okay, so the plane accelerates down the runway and 29 seconds later is moving at positive 72 meters per second, where the plus sign indicates to the right. Okay, determine the average acceleration of the plane. All right, so if we want to do that, we don't have to manipulate the formula at all. We can just say A equals VF minus VI over T. Okay, we're told the time is 29 seconds. Okay, we're told the initial velocity is 0 meters per second. We're told the final velocity is 72 meters per second to the right. Okay, and we're just being asked to find A. So we just have to plug in our numbers, agreed? just like a graphing question from the other day. All right, so we would have positive 72 minus 0, okay, divided by 29, and that should give us 2.5 meters per second squared to the right. Yeah, when the question says positive indicates to the right, right is the more specific direction. Right is what we write on there for our direction. Okay, everybody with me there? Okay, meters per second squared means meters per second per second, the rate at which we change our velocity. Keaton, question?
I have different numbers than that.
Okay, you do. How?
As in it doesn't say it attains a velocity of 72, it says it attains a velocity of 260.
Oh, kilometers per hour. I changed it to meters per second on here. Sorry, yours says kilometers per hour. If you divide 260 by 3.6, you should get 7.2, or 72, sorry, meters per second. Okay, so I did change it in my notes, but I think I forgot to change it in the notes package. Okay, we don't want it in kilometers per hour. Okay, all right. Other than that, questions on how that formula works? Okay, like I said, we've already used it in that form with our velocity versus time graphs. What we're going to look at going forward here is how do I manipulate it to solve for things other than acceleration? Now we're going to need all three rules, just like we did for y equals mx plus b. Okay, because where does this formula come from? Right, this is still this is y equals mx plus b, right? Okay, when we have our acceleration, or velocity versus time graph, okay, when we calculate m, we're going y minus b over x, right? It's the same format. On this graph, y is final velocity, b is initial velocity, x is time, okay? The slope of that graph is acceleration. That's where that formula comes from. I don't know why I drew that. Okay, and we've already gone over this because we explained where the units come from, so that we can skip. Okay. Let's talk manipulation here. So let's say I want to solve for t. Do I want to leave it where it is, or do I want to move it? I need to move it because right now it's on the bottom and I can't solve for it on the bottom. Same as it would be if it was v equals d over t, right? I wouldn't leave it on the bottom. Okay, so I'm going to have to move it over to the other side by multiplying, right? Because right now I'm dividing, the opposite is, okay, so it comes over here, right? Now what do I do with a? Okay, so a comes over here, manipulation is done. Okay, so solving for t, pretty straightforward. All right, I want to solve for VF. What should I move first? T. I want to move what's not attached. Right now, VF and VI are attached, right? T is beneath them. I would do the top before I divided it by T. Agreed? That makes them attached. Okay, so I'm going to move T over to this side. Okay, now I can move VI. How do I move VI? I add VI to both sides. Okay, before I move VI, I want to kind of talk through this logically. Okay, on this side here, we have T times A. And they're telling us that that equals the change in velocity. Okay, so T times A equals the change in velocity. Now, I'm going to add VI over to this side. Does it make sense for my final velocity to be my initial plus the change?
Yes.
Yeah. Okay, so if you're a person that likes to have stuff make sense like word-wise, okay, hopefully that helps you a little bit with the manipulation. If I take my initial velocity, I add the change in velocity, that should give me my final velocity. Okay, it's just like if you go to work with $5 in your pocket, okay, and then you work for 8 hours and you make, I don't know, how much money you make at work, $100, okay, we'll just say you make $100 at work, okay, at the end of the day you have $105. Here's what I started with, here's how much I made during the day, here's my final money, okay, minus, you know, extortion and all that kind of stuff that comes off of it, okay. All right, let's go back to our original formula here. Here's the trickiest one. Now I want to solve for VI. What should I move first?
T.
Still want to move T first. Okay. Now what? Okay, I can. That is one way to do it. I can subtract VF. So what I would do is just move this over here, okay, and then subtract VF from both sides. Here's the problem with that. What am I solving for? Negative VI. And that's fine, as long as you remember that what you get for your answer is actually the opposite direction that it's supposed to have. Okay, some people are fine to do it that way, I'm not. Okay, I always forget, okay, that I've solved for a negative and then I get the direction wrong. So here's what I do. Okay, it's gonna seem a little bit backwards, okay, but here's what I do. I actually add VI over to this side. Okay? Now, according to order of operations, would I multiply T by A before I add it to VI? So does that mean it's just a number? Can I subtract that number over to the other side? Now VI is positive. Now I don't have to worry about what direction I get. It's going to be the right direction. And if you're one of those logical, I want to hear it in words kind of people, if I take my final velocity and I subtract how much I changed it by, that should get me what I started with. Agreed? Okay. Does that sort of make sense? That's the trickiest manipulation. Okay? There's more than one way to do it, and they're both equally valid. You could solve for negative VI. You just have to remember that that's what you did. This solves for positive VI. Okay, questions there? Okay, that's all the manipulations of that formula. There's only got 4 parts. There's only 4 things we can solve for. All right, I want you guys to write that one down. Okay, we're going to do what we always do when we get a new formula. We're going to do one problem for each manipulation of that formula just so that we see how it goes. And you've got 4 examples. Okay, record them in your notes for later. So I'll give you a minute to get that written down, then we'll walk it through. Yep.
I think the ones are a bit messed up because, like, for the printed parts, lots of the images are covering the words.
Did the formatting change?
I don't know.
Oh, yeah. Something like that with my formatting I didn't notice. Sorry about that. Okay. All right, so let's look at question number 1 here. So the sprinter starts from rest. What did they tell me? Initial velocity is 0, right, because they started from rest. Okay, and they reach a velocity of positive 16 meters per second. What did they give me there? V final, right. Okay, and that took 4.5 seconds, so that is time. Okay, and they want to know the acceleration. Okay, so again, this is why you get a mark for givens, right? It helps you decide what formula to use when you're on the unit exam and every formula on the back of your periodic table is now in play. Okay, so A equals VF minus VI over T has all 3 things I was given and the thing I was looking for, so that's the formula I want to go with. Okay, so I'm looking for A. All I have to do is plug in my numbers here. There's nothing complex about it. Okay, I'm just going to go 16 minus 0, okay, divided by 4.5. Okay, forgot to start my calculator. It's going to be what, like 3.1, 3.2?
3.5.
Was it 3.5? Okay, see, my estimating is not too good today. Okay, so we're going to have 16 divided by 4.5, and that's going to come out to 3.5, what are my units? Meters per second squared. Okay, what else do I need on that number? It's positive, right? Okay, acceleration is a vector quantity, and they told me positive in the question. Okay, so it's got to be positive for me. Okay, so let me see, guys. Just 16, okay, divided by 4.5. Okay, that actually should be 3.55. Actually, 3.56. Okay, is what we should get there. Okay. Everybody with me on that one?
Mm-hmm.
Okay. Anyone need that one up anymore? Okay, write this one down and give it a try. Different manipulation. Okay, I'll give you a few minutes to try it on your own and then we'll walk through it together. I don't think you guys will have much trouble with it, but we'll walk through it anyway. Okay, so on this one here, it's asking me how long something's going to take. What am I going to be solving for?
Time.
Time. Okay, so a jet to accelerate from rest, what did they give me? VI. Okay, and to positive 85, so that would be VF. At a rate of positive 22 meters per second squared. Acceleration. Okay, so I've got 3 out of the 4. Okay, I know I'm going to use this formula, A equals VF minus VI over T, but now I'm going to have to manipulate this for T. So what do I do with T?
Times it.
Right, multiply both sides by T, so I'm going to have T times A equals VF minus VI, okay, and then what am I going to do with A? Right, divide both sides by it, okay, so I've got that, and then I just have to plug in my numbers. So positive 85 minus 0 divided by positive 22. Okay, so 85 divided by 22. All right, tells me that's going to take 3.86 seconds. Okay, questions on that one? All right, try that one. Still write it down as an example here, but give it a try after you write it down. Okay, so this question very nicely tells us exactly what we're looking for. What is the final velocity? Okay, so we're looking for VF. Okay, questions won't always do that. Sometimes they can be worded kind of cryptically. Okay, of a race car, if it starts at positive 15 meters per second, so what do they give me there? Initial velocity, or VI. Okay, so positive 15 meters per second. Okay, and it accelerates at positive 7.2 meters per second squared, so they gave me acceleration. Okay, for 6.5 seconds. Seconds is time, so, all right. We don't have VF. We are going to have to use this formula, VF minus VI over T. What do I move first? T. Okay, so A times T, it's not attached. Okay, is VF minus VI. What do I do with VI? Add it over to the other side. Do I really, whoops, that's not 0, that's supposed to be a question mark. Okay, when I move this over, I want to add it. Okay, so I'm going to have VI plus A times T equals VF. All right, so I'm going to have my 15 plus 7.2 times 6.5, okay, gives me VF. Should VF be bigger than VI in this situation?
Yeah.
Yes, it should. Okay. Always little things to ask yourself. That way when you type in the stuff in your calculator, you know if the answer makes sense or not. Okay, so 15 meters per second plus 7.2 times 6.5. All right, 61.8 meters per second. And I do need a positive beside that because I was given positive as a vector in the question. Okay. Everybody all right with that one? Okay. Okay, we'll do that one, then I'll give you a little break, and then we're going to try some where vectors really come into play. All of these ones, everything's been going forward. Okay, we're going to go into a few where maybe the direction changes. This one's still just a forward. Okay, so this one's asking how fast a boat was traveling initially. What are we looking for? Initial velocity. We're looking for VI. Okay, if it accelerated to positive 30 meters per second, what did they give me there? They gave me final velocity. Okay, because it's in meters per second, not meters per second squared, right? Always something to look for, because it's easy to confuse the two in a question. Okay, at a rate of 2.6 meters per second squared. There's my acceleration. Okay. it does that for 8.9 seconds, so that would be our time. All right, so we know we're back to this formula here, okay, VF minus VI over T, okay? First thing we want to do is move the T, so we'll have A times T equals VF minus VI. Now, your choice for which way you want to do this, but I'm going to add VI over to this side so that it's positive. Okay, and then I am going to subtract A times T over here. So I've got final velocity minus the change in velocity equals my initial velocity. All right, so that'll be positive 30, okay, that's positive, minus 2.6 times 8.9. Better put in the right numbers. 2.6. Okay, so its initial velocity was 6.86, that's positive, meters per second. Right, so it was already moving forward when it started to accelerate.
How come we don't have the vector velocity anymore?
We do, positive. Oh, sorry, because I don't write it on. In the acceleration formula, it could be velocity, it could be speed. I've just been lazy and not put it on. Okay. In the end, for this one, I'm less worried about it than I would be if I'm asking you speed versus velocity and a V equals D over T question. But you're right, it should have the little arrow over top. Okay. And so should acceleration for that matter, because it's also a vector quantity. Okay, I'm going to give you guys about a 3-minute break here, and then we're going to work on some that have, maybe a change in direction, other little things that we have to kind of keep track of in the question. Okay, this is an acceleration problem, but now vectors are going to be important, and you will have to establish what direction is positive and what direction is negative. There isn't a right or wrong for that. You can decide whichever you want as long as it's consistent. Okay, so the ball is initially rolled up the hill, but like all things that are rolled up a hill, it's eventually going to what?
Coming down.
Yeah, but the whole time it's going to be accelerating which way? Down the hill. Once it leaves your hand, it's all gravity after that. Okay? Okay, so anytime I get a question where I think the direction's going to change, I draw it out. Okay, so I've got this ball, okay, and I'm going to say that up the hill is positive, okay, and down the hill is negative. If you made it the other way, it's fine. Okay, all right, so on this one here, we know it's rolled up the hill at 4.5 meters per second. That's going to be my initial velocity. Okay, it accelerates down the hill at 2.1 meters per second squared. Well, down and up are opposites, so that means my acceleration is going to have to be negative in this problem. All right, what's the velocity? So we're looking for final velocity after 3.5 seconds. All right, so I'm going to use my acceleration formula here. A equals VF minus VI over T, but I'm going to manipulate for VF. So multiply both sides by T, add VI, okay, we're looking for VF. So VI was positive 4.5 plus 3.5 seconds times negative 2.1 meters per second squared. Important that I have the negative in there. All right, so 4.5, and we're going to have plus 3.5 times negative 2.1. Okay, does it make sense after nearly 4 seconds, or after 3.5 seconds, for the ball to be going the other way? Yeah. Okay, I mean, every second it's accelerating down the hill at 2.1 meters per second squared. Well, it only started out at 4.5, so after just a little more than 2 seconds, it's going to be going the other way. It's going to slow down for an instant, come to a stop, and then start rolling backwards down the incline. Okay, so that answer, okay, of negative 2.85 does make perfect sense, except I'm not going to leave it as negative. Negative represented down the hill. My final answer has to be 2.85 meters per second downhill. Guys, that comes up all the time. Okay, where you mathematically have to plug in positive and negative into your calculator because you can't type in uphill and downhill, okay? But then you have to remember when you're done that you have to transfer that back to the directions the question gave you. If the question gave you positive and negative, you're fine. But they don't usually. Usually they're gonna say right or left, up the hill, down the hill, north or south, and you're gonna have to transfer positive and negative back to those original directions.
So you would have to choose which, like, if positive is left or right?
Exactly. Okay. Usually what we do is we kind of go with a standard X, Y kind of scatter plot, right? So up is always positive Y, right is always positive X, down is always negative Y, and left is always negative X. It's but you can do whatever you want as long as at the end you transfer to right or left or up or down or whatever. Can't use a triangle for this formula. Okay, just a reminder, no triangles. Okay, let's make that one our last one for today. Okay, so object is thrown up in the air at an unknown velocity. It is in the air for 6.5 seconds, and its final velocity is 2.4 meters per second down. Acceleration due to gravity is 9.81 meters per second squared. What is the initial velocity of the object? Alex, question?
Are these the type of quizzes or questions we have on the quiz tomorrow?
No, tomorrow's quiz, as I said, is just on graph.
Alright.
So you have 3 graphs, I think, 3 graphs tomorrow. So position versus time velocity first. Okay, so the trick in this question, it's not really a trick, but it's something you have to catch. The object's initially thrown up, which means its initial velocity, even though we don't know what it is, we do know what direction it's in. Okay, up is positive, right? It does tell us that the final velocity is down, and then it tells us the acceleration. But it doesn't tell us the direction of the acceleration, because it's gravity, and we should know it already. Okay, that gravity brings you down. It's always holding you down. Stupid gravity, always working against you. Okay, so acceleration is going to be, and I'm just going to say up, positive, down, negative, just to put that in there. Okay, negative 9.81 meters per second squared. Okay, we know that VF is 2.4 meters per second, also negative, and we know the time is 6.5 seconds, so it's a pretty good throw to have that kind of hang time. Okay, and we're looking for VI. All right, so A equals VF minus VI over T, multiply both sides by T, add VI to both sides, and then subtract T times A. So we got VI equals VF minus T times A, so negative 2.4 minus 6.5 times negative 9.81. So are we going to be subtracting a negative number here? Is that going to help me get the positive number I'm supposed to get?
Yes.
Absolutely. Okay, so negative 2.4 minus 6.5 times negative 9.81 should give me that, wow, this guy has an arm, okay, 61.37 meters per second. That is major league kind of arm. Okay,
wow.
That's really fast.
I was wondering what I did wrong to get over 60 meters.
Yeah, pretty fast. Okay, I'm not sure why people are in the hallway. That's weird.
They're massive.
Whoops. We were supposed to be at maths. Thank goodness no one saw us. Sorry, I totally forgot.
Well, at least we're a class ahead.
The forgiveness has to come to me. It's not your fault. I'm the one who forgot. Okay? I got so excited about the acceleration lesson.
Yeah, we're a class ahead now.
Yeah, okay. It's not the first time I've done that.
Not the first time.
Well, I mean, you're going to miss the unit exam, so you'll have to write that after Christmas. And then, well, you'll miss like the first 2 days of the unit. It's not going to be much. Just make sure you're watching on Google Classroom. Do everything we do. You're probably going to miss another lab, so I'll have the data. You'll be able to do it from wherever you are, and just submit it on Google Classroom. So and you're going to have access to Wi-Fi and everything. Okay, where are you going? You're welcome.
Thank you.
You're welcome.
I mean, at least we'll be in class. Thanks for teaching.